So usually the weather is better in Pisa this time of the year, but you know, I mean, yeah, those who could make it are going to miss a good morning. Okay, so there are a few announcements that I have to make just before we start the real conference. So I want to say first that we are going to be recording the talks. So all the speakers will have to sign a form saying that they agree to be filmed. And if you don't want to be filmed, just say no, it's fine. We're not going to torture you, but you know, you are obliged to sign it. Another thing is that just saying. Okay, so there is a folder there. So in case you haven't grabbed yours, please grab it. And next to it, there is also a list of names. So you should sign next to your name so that we know that you're actually here. And there is also the list for the social dinner, to which I will be talking in a second. So in your folder, you will find a virtual pin that works for the canteen. So during this week, you'll have access to the canteen of the Scuola Normale, which is like 5 minutes walking away from here. And you've got access for lunch and dinner. And it's so you should have a virtual pin. It's 2 sets of numbers. And it's pretty straightforward how it works, but if you can't make a way out of it, just ask us and we'll help you. Anyway, we'll all walk towards canteen together today, so if you have no idea where it is, you'll see that it's really easy, so you can't miss it. Okay, then about social dinner, the social dinner will be on Thursday night, and there is a list there, so you should sign if you want to come, and you should check whether you want meat, fish, or vegetarian option, and the menu is right after it. So unfortunately, you can't have both meat, fish, and vegetarian. You just have to choose one, but you can steal food from your nearby neighbor during dinner. Another thing is that today we're going to have a poster session at the end of the day with a welcoming aperitive. The poster session won't be here. It will be in the main building of Scuola Normale Superiore, which is in Piazza Cavalieri. And Piazza Cavalieri, even if you have never been to Pisa, you immediately see what it is, because it's clearly the main square of the city. And the building of Scuola Normale is the most beautiful building in the square. Anyway, we'll all walk from here, so again, you can't miss it. It starts at 6, and it goes on for a while. So there will be posters, please come, and there will be an aperitif, so you are all encouraged to come and chat with the students and let them explain the posters to you. And yeah, I guess that's it. Another thing is that there is the poster to the conference there, so if you want to have a copy, just grab it. And yeah, I think that's it for the announcements. And so I think I should pass the microphone to Stefano Marmi, that is the director of Centro de Giorgi, that helped us organizing the conference. So thank you.
Okay, so thanks a lot for being here. I'm just here to greet you and to wish you a great conference. So the Centro de Giorgi is by now 18 years old. It's the research center of mathematicians in Pisa. It includes, under the same institution, the Scuola Normale, which is the main stakeholder, but also the University of Pisa and the Scuola Sant'Anna, which are the 3 universities based in Pisa. It started its activity in 2002 with a workshop on dynamical systems, and I'm very happy that dynamical systems, which is my field, is one of the main leitmotif of the activities of the center. It's not the only one, of course, but I mean it has been always and constantly contributing to the scientific success of the Giorgi Center. And I'm extremely grateful to the organizers of the workshop for bringing you here, and the Giorgi Center can't work without not only the contribution of the 3 universities, but also without external funding. And this activity, all the activities we organize are always somehow also supported by external funds. So we acknowledge for this workshop, of course, the generous contribution of the ERC project Intermediate Chaos whose principal investigator is Sasha Bufetov, and also contribution from the Istituto Nazionale di Alta Matematica through its analysis branch. That's it. So. And the University of Pisa. Well, the University of Pisa, so it contributes squarely. I mean, through the center and independently. Okay, thank you, Carlo. So thanks a lot. Thanks to really deep thanks to not only to the scientific committee, but also to the dedication of the local organizers. Who always do a great job, and I'm really. We wouldn't be able to organize all the activities without the commitment of people, and in this way. Okay, thanks a lot.
So, okay, good morning everybody, and welcome to the Scuola Normale Superiore di Pisa, founded by Napoleon. And we start our morning session with a talk by Dmitry Dolgopyat from the University of Maryland, who will tell us about local limit theorems in dynamical systems and applications.
Thank you. Okay, thank you so much. I hope you could hear me. It is a great pleasure to be in Pisa, and my talk today is going to be devoted to local limit theorem and the mixing, and most of what I'm going to tell is joint work with Peter Nandri from University of Maryland. So the title of this conference is From Order to Chaos, and it's very kind of a popular topic in the modern world. So I would like to present some results on this subject. And so what in particular our emphasis here on dynamical systems. So what we know that there are many dynamical systems which exhibit chaotic behavior, and so what are the main hallmarks of chaos for deterministic systems? So one is mixing. So let me recall that if you have some map T from some space X to X, and which preserves probability measure, so invariant probability, invariant probability measure. When we have mixing, means that the mu of A decomposed with Tn, so this converges and goes to infinity. Now it's better. Want me to use another microphone?
This one. In this moment.
Okay, so this one is working better? Okay. Fine. So the definition of mixing, I guess, if you haven't heard, you can try to recall by yourself. But this is the mixing means that we have asymptotic independence between the present and the future, and so this is one important property, which means that the dynamical system is stochastic, and another property, and we should call it, say, for A, B, say, in L2 of mu, or some dense subspace thereof. And another important property is central limit theorem, CLT. So this means the following: if we have A from X, some observable on our space, when we can consider A sub n, which is ergodic sum, so sum k from 0 to n minus 1, A of tkx, and with some, suppose with function mu a has zero mean, when what we want, CRT means that the measure of points such that an divided by square root of n belongs to some interval, say, from a to b, converges as n goes to infinity to integral from a to b of the Gaussian density. So Gaussian density, so z is like 1 over 2 pi sigma e to the minus z square over 2 sigma square. And so this central limit theorem says that if we have an observable, then ergodic sums behave the same way as the sums of independent random variables, identically distributed random variables. So this is kind of two properties which are shows that the system is in some sense close to, like if we consider A, or we consider, we sample our system along the trajectory of the dynamical system, it behaves in many ways as sequence of independent random variables, has many of the same properties as the sequence of independent random variables. And central limit theorem says that allows us to control the probability that ergodic sums hit the interval of size square root of n. And for some applications, we want to allow we want to say that the left-hand side and right-hand side have the same order of magnitude for shorter time intervals. And so this is equations which is usually treated by local limit theorem. So let me maybe start with the following result, which was, I guess it's proven maybe by, so the first part was maybe due to Sinai, and second part, we just central limit theorem says that let us consider the most chaotic example, say, suppose that T, let's say, transitive axiom A diffeomorphism. And mu is some Gibbs measure, for example. I'm saying to say a smooth measure or measure which has smooth density of unstable manifolds. And when the first result, let's say part A is due to Sinai, says that if we have A and so with central either so we have the central limit theorem holds, and part B is due to Giorgi and Hardy, and it gives local limit theorem. So local limit theorem, we know, has two parts. One is arithmetic and the other is non-arithmetic. So it says that there are two possibilities. Either we have for any sequence Zn such that Zn divided by square root of n converges to Z for any interval of size L. What we have that probability that An belongs to the interval of size from Zn to Zn plus L. This behave times square root of n should behave like L times the Gaussian density of Z. So if a local distribution looks looks like Lebesgue, or the second possibility that there exists some function B such that after we modify A by, and maybe there exists some A H real, so B from X to R, and there exist some numbers A and H such that if we modify our A by a coboundary, so we can write B of x minus b. So is equal to a plus, can be written in this form, a plus b sub x minus b of tx plus a tilde of x, and a tilde belongs to hz. And in this second case, we have the following. Suppose that we have a sequence Zn such that Zn of the square root of n belongs to, it converges to Z, and Zn is admissible, so Zn belongs to Hz, when probability of a measure of points such that the ergodic sums of this modified function an are equal to Zn times square root of n converge to h times the Gaussian density. So we have two possibilities. Either we have non-arithmetic local limit theorem, or we have arithmetic local limit theorem. But arithmetic local limit theorem holds not for A, but for A modified by co-boundary. So if we want to recover the original distribution, so this allows us to control ergodic sums of A tilde, so which is different. So we know that an is equal to n times a plus b minus b composed with t sub n. So if we want to control plus a, the ergodic sums of a tilde, so if we want to control a, we also need to see what is the value of b and what is at the beginning point and at the end point. So we have something which is called mixing LLT. Moreover, what we have that if we take a measure of, say, some functions b1 of x, b2 of t and x, indicator of zn, indicator an tilde equals to zn, when this times square root of n, this converges to h g of z, measure of b1, measure of b2, provided that b1, b2 are almost continuous. So almost continuous means that the set of discontinuities has measure 0. So we want to take, for example, b1 belongs b1 to be the set where b belongs to certain interval, and b2 be the set where b belongs to some other interval. So this statement is called mixing local limit theorem. So mixing local limit theorem, maybe we can also abbreviate MLLT, allows us to, starting from ergodic sums of A tilde, now get information about ergodic sums of A itself.
Excuse me, the moreover statement only concerns the arithmetic case.
Yeah, so there is also moreover statement in similar statement holds. Yes, thank you so much. Similarly, statement holds for in non-arithmetic case. So in a non-arithmetic case, we of course have not counting measure but Lebesgue measure. So again, we can put here indicator of
an interval.
Yes, of the interval. So this is the thing which we one has. And so, as I mentioned, so what we see, this mixing local limit theorem, it includes usual local limit theorem if we just take b1, b2 equal to 1. And it also morally includes usual local limit theorem, but it also morally implies mixing if we sum over all possible values of Zn. And this is just because here we have to integrate with respect to Z, and Gaussian density integrates to 1. So we get mixing. But of course, the caveat is that one needs to be a little bit careful, because local limit theorem usually holds only for Zn being, the convergence is usually uniform for Z being in the compact set, so one needs to be a little bit careful when one wants to derive mixing from LLT, but just morally speaking, mixing LLT includes both mixing and LLT at the same package. And
Sorry,
theorem, you just assume transitive axiomatic homomorphism?
Yes.
Mixing?
Yeah, mixing. Yes, sorry, maybe mixing. Yes, sorry. Yeah, maybe you need mixing. Yeah, thank you. Maybe topological mixing. Yeah, because otherwise you need to do. Yeah, no, otherwise I guess you have to have some. Otherwise you have to consider powers of t when you have. Yeah, thank you so much. So now what we have, we want to discuss. I want to discuss today is maybe relation between these two notions, local limit theorems and mixing. Local limit theorem and mixing in in the setting of dynamical systems. So there are a few applications of local limit theorems, and I want to start. So we were following simplest one, the most straightforward one. One could consider, say, suppose we are in the arithmetic case. So suppose A takes values in Z. A is A from X to Z is integer valued, and when one can associate to this dynamical system as Q product, so F, which acts on M, which is X cross Z into itself, and this map F acts of F of X Z is T of X Z plus tau of X, and then this preserves some infinite measure nu, so nu is going to be nu cross-counting measure, cross-Haar measure, and then for such this measure, so measure of the whole space is equal to infinity. So for such systems which preserve infinite measure, there are several notions of mixing. So one popular notion is Kricke-Berg mixing means that the following. So we say that the system preserving infinite measure is Kricke-Berg mixing if there exists some sequence ρ of n such that if we consider mu of A and B composed with Fn of X, so composed with Fn, this should be dividing by ρ of n. This should converge to nu of A, nu of B. So this is just so this function ρ of n is typically going to 0. So we say that because there are a lot of room in our space, we could basically most of the mass escapes to infinity, and so we want to see that mass. So this AB should be say in some Banach space B, which is we want to be usually so in L, say L2. So we want to have some regularity, and we want to be this function to be integrable.
So excuse me, F you assume it to be conservative or dissipative?
So this does not. So this can hold for like this. Like yeah, this is important. There are several notions of mixing, so it does not usually in general. In some of them, most of them do not imply conservativity. For example, if you consider underwalk in ZD, is going to be mixing in this sense, but is not going to be. Yeah, so what one can show. So let's see, maybe let me do here B1, A1, A2. Let me put A1 here, A2 here, and so now in this case, suppose we take A1 of XZ, AJ of XZ to be indicator Z is equal to ZJ. So we want to localize Z coordinate, and when times Bj of X, then you can see that this Kricke-Berg mixing follows from local limit theorem, because just this is just we want to compute the left hand side. We want that ergodic sums of our function tau should be equal to z2 minus z1, and then we also have some restrictions on b1 and b2. So this is exactly a local limit theorem gives this notion of Krickenberg mixing.
With what rho n?
With rho n, so here in Z, rho n is going to be 1 over square root of 1 over 2 pi sigma square root of n. And general in dimension d, you have to take the power d, and you take determinant of corresponding matrix. So and so this is very easy to see in their arithmetic case, and it is slightly more involved if one has non-arithmetic case. But so in the non-arithmetic case, one has consider x cross r, and one can consider the same kind of question. And again, one can show that with a little bit more work with local limit theorem implies with Krickenberg mixing. I want to maybe present similar argument in slightly different setting. Basically, we know that properties of skew products are very similar in many cases to properties of suspension flows. So let me just recall the corresponding settings. So let me call that if you have t from x to itself and tau is some roof function, we can associate suspension flow, which may be called S sub t. So suspension flow on say space omega. So omega is going to be x cross r modulo identification such that the point x s is identified with point t of x s minus tau of x. So the picture is like this. We have this roof function tau, and when we go and when s t of x s just x s plus t, so we go up until we reach the roof, and then we jump to point t of x 0, and then we go up, and then we jump to t square of x 0, and so on. So this is suspension flow, and we want to study mixing properties for this suspension flow, and we suppose tau satisfies mixing local limit theorem, and we want to see if the suspension flow is mixing or not. And so suppose we have none. So maybe let me first suppose that this local limit theorem is non-arithmetic, and then we take some observables. So let me take observable ij as before indicator that S belongs to aj plus aj, sometimes function bj. So this is of S, this is of x. So as before, I take this product function, and I also let me assume that h1 is much smaller than h2. So which means that I have so here a2 plus h2, and I want if a point here, some point from this interval, I started from interval, very narrow interval from a1 plus h1, and I want if my orbit is inside this interval, then most likely the whole interval should be inside. So this one can easily reduce the general case to this case. And so what is the formula for suspension flow? So if we have some time, we start with point xs, and we are given some point t. What one needs to do is one has to find such n, such with tau n of x, where ergodic sum of x should be less than s plus t, but not less than tau n plus 1 times x. And when the point st of xs is going to be tn of x, s plus t minus tau n of x. And we want, basically s is very close to a1, so we want a plus t minus tau n belong to interval from a2 to a2 plus h2. And so this means that tau n should be from a1 plus t minus a2 minus h2 to a1 plus t minus it. It should belong to this interval. And so if we want to compute this integral, when so if tau belongs to this interval, then so we want to compute mu of a1, a2. So this, sorry, maybe I need to recall that this mu is going to be preserving the measure. Mu is actually d nu is equal to d mu of x. S is going to be d mu of x ds divided by tau, mu of tau. And then, if we want to compute this integral, then what we have is that this is going to be 1 over mu of tau coming from here. And then we have, if we have mixing LLT, then we have so mu of B1, mu of B2, H1. So this is just from this H1 is from the property that if point x s belongs to this interval, then the whole interval belongs to this interval, and then we want to have sum over n of so 1 over square root of n times the Gaussian density of t minus n times mu of tau divided by square root of. So maybe with some, so this Gaussian density corresponding to standard deviation sigma. So now what we just need to do is to perform this sum over n. And so how we perform this sum, what we expect that the main contribution comes with, for main contribution to come if n is over n times mu of tau should be of order t. In this case, n should be of order t over mu of tau. So if you replace here square root of n and here you replace with square root of n by t divided by mu of tau, then you have that 1 over n square root of n g of so t minus n times mu divided by square root of n is going to be approximately 1 over square root of t divided by g sigma or tilde of zn, where sigma tilde is going to be sigma over mu of tau, and we want maybe to here zn plus 1 minus zn divided by mu of tau, and where we have this notation, sigma tilde is going to be this, and zn is going to be n t minus n sub mu divided by square root. So if we do this, and we see that here we have a Riemann sum of Gaussian density, when the summation is going to be H2 coming from the local limit theorem, so it's going to be H1, H2 mu of measure of average value of B1, average value of B2, and then we have mu of tau squared coming from one mu of tau comes from here and one mu of tau comes from here. So we get that this is equal to integral of A1 times integral of A2. So this is we see that if we have a local limit theorem, non-arithmetic local limit theorem, when we have mixing, and so arithmetic local limit theorem is can be analyzed similarly. So what we have is one the result which we have the joint paper with Peter Nandri says, suppose where T satisfies mixing local limit theorem plus some appropriate large deviation bounds. So then we have the following statements are equivalent. The following statements are equivalent. The first statement is ST is mixing. Second statement would be ST is weakly mixing. And the third statement would be LLT is either non-arithmetic, so you will have non-arithmetic case, or maybe AN we have or arithmetic. So arithmetic means what we have A n can be written as B, A can be written as B minus B composed of T, plus A and plus A tilde, where A tilde belongs to H sum Z, and then in this case we want A over H to be irrational. So if A, for example, is rational, say for example A is equal to 0, then we clearly have some arithmetic abstractions for this inequality here. We only can get this if T is, if we start very close to 0 and we want to count very close to 0, then we only can do it if T is integer. So, and this says that this local limit theorem implies this mixing in the under appropriate assumptions. And here we have had large deviation, some large deviation estimates, because this is, say that the main term comes from here, but we need to have some way to say that for n which is not coming from in this range, the contribution is small. So I will maybe mention later what kind of large deviation bounds we need. And so this is maybe not very interesting as long as you just with assumptions just made so that the proof works. But the question is if one could really check with assumptions under some reasonable conditions. And I will give some examples. Maybe before doing so, I want to mention some extensions of these results. And so the extensions which so before making this extension, maybe just one notation which is going to be useful. I want to have so L of G is going to be R if non-arithmetic case, and otherwise this is group which is generated by H, and H if we have arithmetic case. L is linear group, because basically what non-arithmetic local limit theorem says that we are going to be, that after change of variables, our observable takes
Sorry,
place.
what is AH? I missed this.
Like it is here from this.
No, that symbol, what does it?
Is the group is the smallest is
the
group closest the small closest closed subgroup generated by
Okay.
A. And so in any case, with L of G is the smallest closed subgroup, such that for any phi, for any B, if we consider A tilde, which is A plus B minus B composed with T, when we want that A and tilde should belong to L of G for all. So this is going to be just abstract definition of a linear subgroup. So if we make, and when the statement mixing, so what we know, what we say that the mixing is equivalent to saying that A of G is equal to. So A of G is either R or Z. Oh,
Mixing and weak mixing also, right?
yeah, weak mixing.
Both of these are also equivalent to weak mixing. Yeah.
Yes. So this is what we have, and and otherwise L of G can be equal to can be equal to Z, or if L of G is 0, this means that the function is equivalent. And so we have two extensions which I want to mention of this result. So one extension means that we could allow, we can have more general local limit theorems, not necessarily Gaussian local limit theorem, but maybe some conversions to the stable law. So let me give some example. So suppose that tau, the probability that tau is large, is going to behave like t to some power alpha, where alpha is between 0 and 1. And when it is, so this, in this case, nu is infinite, is going to be, so mu of tau is going to be infinite. And then, so we have this suspension flow is going to be on the infinite measure case, and in this case, what one expects with correct scaling for the periodic sums of tau should be n to the power 1 over alpha, and then this should converge to some stable laws. And in this case, what we have, theorem 3 can be is the following result, that if so this conversion star can be upgraded to mixing local limit theorem. So we have mixing local limit theorem, and in addition, what we have.
Sorry, I missed. What's written there with the star? Tau n over n over.
To power 1 over alpha converges to some stable law.
Converges how?
Weakly. But we want to have a mixing local limit theorem, means that probability, say non-arithmetical local limit theorem would be mu tau n belongs to z plus a is going to be should behave like a over n to the power 1 over alpha times z and some rho, which is density z, and rho is density of appropriate stable.
So you're considering a conservative flow of infinite measure.
Yeah, this is a flow of conservative with infinite measure. So we assume this and plus large deviation bounds. So maybe large deviation bounds would be something like this. So this holds provided that Zn over n to the power 1 over alpha should be greater than epsilon. The convergence is uniform in this range. And then we have large deviation bound. And then we have some large deviation bounds, which would say, in particular, that without this assumption, we work with mu or zn, tau n belongs to some interval t plus a, should be bounded by some constant t to the gamma 1 n to the power gamma 2, and we want gamma 1 to be less than 1, and gamma 1 plus alpha gamma 2 is equal to. So this is like appropriate large deviation bounds, so here we don't make assumption about it. So interesting case when n is very small, t is very large, so n is small compared to t. So for example, we don't want to have large probability of just after one step hitting t plus a, hitting this interval. If this holds, then this suspension flow is Krichtenberg mixing. And then what else happens?
With rate? With rate?
With rate. Rho and rho n to be equal to some constant n, some kind of which involves alpha function and alpha. And again provided with L of L of tau, L of tau is the whole group is the linearized group is the whole, and again if the group is not the whole space, then the statement does not. And maybe one more result to mention is we want to start with local limit theorem for the dynamical system, and then we want to have local limit theorem for the flow. So we have A not omega to R some observable. So we are in the same setting as theorem 2. We have a usual central limit theorem, and we have some observable, and then we consider A sub t, which is going to be integral from 0 to t A of x g t plus t of so integral, we want to consider ergodic integral, and then again we consider a bar, which is going to be integral from 0 to tau x is x to s ds. So this is what happens once we do one with this inside one before the next jump, and then again theorem 4, which is going to be joint work with Peter Lander again, states in this case A satisfies mixing local limit theorem, provided that we have pair A tau satisfies mixing local limit theorem. So we have mixing local limit theorem for diffeomorphism. We can obtain mixing local limit theorem for flows, and when this plus large deviations bound, and so large deviation bounds will be, say, for example, probability that this pair A bar tau n is belongs to some minus some z belongs to some ball of radius r, should be less than some constant over r, divided by n to the power n squared, square root of n squared, plus times Gaussian density, and plus some C1 with some other constant times n2 conforms. And so here, this is what the main of which we expect in the compact range, and this is some bound, some upper bounds, and it's 1 plus. Delta some kind. Typically, one can check this with delta equals and provided. And there is one more assumption that now linearized group of this pair in bar tau should be either R or should be equal to R or R cross V. And one more assumption that ST is mixing. So supposing that suppose that ST is mixing, we know already what is this Ricerca conditions for mixing. Then if the linearized group is either R2 or R cross Z, then we have mixing local limit theorem for flows. If this group is Z2, then in general, it may be by chance that local limit theorem holds, but most often you expect that this right hand side to be periodic functional. So you would not expect usual local limit theorem if the group is small. So, and when some examples, so that when we need to check, to have some assumptions, some examples of the systems which satisfy our assumptions. So examples may be axiom, axiom A flows. And one example, we can consider suspensions of homomandal maps. So this map, this is expanding map, which has new fixed point, which is of order so 1 plus, which has some neutral fixed points, and we have some say we can have Lorentz does a billiard system, which periodic extension of Simon billiard of V5 horizon. We can have Lorentz attractor. So these would be examples where these assumptions about large deviations could be valid. So how do I have time?
Yes.
How much time do I have?
2.5 minutes.
Okay, thank you. So this is basically, I wanted to, so this is one application which I mentioned is with Schroedinger mixing. So there are some other notions of mixing for infinite map preserving systems, but it is, and in fact, in these other cases, we found that local limit theorem is also relevant. So one example which we have is to say we could consider Fermi-Ullmann ping pong, which is the system that particle performs period where is a particle which bounces free between two infinitely favored walls, one is fixed, one other moves periodically, say h of t plus 1 h of t, and we consider the k, and the k is known, it is not smooth, not mixing, it has poor mixing property if h is smooth, but we consider h minus h if one discontinuity, for example, h of t equals to a t minus 1 half, fraction factor t minus 1 half square. This is an example which was studied maybe numerically by Ullmann. For such examples, we could discuss also mixing properties of these systems, but we don't have much time. But basically, what I want to say is that there are some relations between local limit theorem and mixing, and so basically similar methods can be used to analyze in both the systems, and so we have some results about relations between local limit theorem and mixing, but it's just for some very stochastic systems, but this is for this notion of mixing. So usual notion of mixing is generalizations to infinite measure, which is Schroedinger mixing, but there are many other questions in the same kind of flavor, and this is kind of interesting topic, but I think I have to finish today. Thank you for
Okay, we thank Dima for a very beautiful talk. So if there are questions, please just allow me to bring the microphone to you so that the question may be recorded. So questions, please. So I have a question. Why do you need the large deviation assumption, and could you formulate it more formally?
Well, there are several large deviation assumptions which are weaker than I have, but basic. So there are several basically large deviation assumptions. Just in weakest one is just to say that, say in the classical local limit theorem, we want to sum to be main contribution to the sum to coming from the compact set. So in the assumption, which is very often can be checked using some kind of anti-concentration inequalities, is this kind of assumption. But and for finite measure case, for infinite measure case, it is this kind of condition which we could check, but this is what we check in applications. And sorry, maybe I want to mention that there is an example even in the case of independent random variables by Lamperti and Garcia, that if these assumptions fail, then the theorem fails. So it is some assumptions of this type are necessary, but in many dynamical systems one could check this assumption. So this is an important step. It's not much.
Any further questions? Oh, yes.
So you mentioned results for suspension flow, so in continuous time. I guess you can do the same for suspension maps in discrete time. So going from an induced map from a mixing local limit theorem from an induced map to a local limit theorem for the original map.
Yeah, in fact, this is. In fact, this is a very good point. That this map, this also works for induced maps because, in fact, like for example, in these examples, to check this condition, usually we first do certain. Say this system admit Young tower, so when one has Young tower for induced map, and when one uses the same kind of version of this for induced maps, such that to get local limit theorem for your appropriate section, and when using the local limit theorem for appropriate section, one can to get local limit theorem for flows. Yes, thank you.
Any further questions? I have one more question. So the local limit theorem, as you formulate it, is it possible to formulate, maybe under stronger assumptions, convergence of densities themselves of the distribution function? Because you, if I understand correctly, you sort of average density over a small interval, but is it possible to assert convergence of densities themselves?
So this is good. Question, but in fact, I don't know. Maybe I just wanted also to mention. Maybe today there is a poster session. So my student Kasun Fernanda is going to give some presentation, and he maybe has some results about convergence of density, but not in the setting of, as far as I understand. So far, he doesn't have any results for dynamical systems about convergence of density, but we have some results in the setting of, say, Markov chains or diffusion processes. But I don't know if one could have some strong statement results which guarantees convergence of densities.
Further questions or remarks? If not, then we thank Dima again. And we resume after lunch.
This afternoon session, and the first talk is by Khanin, and we will speak about Schroedinger operators with quasi-periodic potentials and the Aubry-Mather theory.
All right. Thank you very much for inviting me. It's always a great pleasure to be back to Pisa. And Dima already mentioned that this topic now switched a little bit. When I was much younger, it was more like from order to chaos. And that was topics of all the meetings around, say, 80s. And now it's from chaos to order, and we can reflect later on during our dinner or something what it means for our lives. But I want to start with some old stories. So I mean, this 10 or maybe 15 years from mid-70s to mid-80s were very active period in dynamical systems. It was just several breakthrough happening at that time, and I will discuss them shortly, and then I will connect a couple of them together, try to connect them. But I will start with several characters which I will discuss in this talk, and one will be, of course, Schrödinger equation, Schrödinger operator with quasi-periodic potential, periodic potential, and then it will be maybe I would say general topic is a global KM, and by that I mean few things which not necessarily people would agree at the KM, but I would put here Aubry-Mather theory, and maybe renormalization, and some other things. So, and all this happened, maybe Riemann theory as part of it, which will be playing a role in what I will discuss later. So all this happened starting from early 70s, say middle 70s, and I will first say a few words about the work which was written by Dinaburg and Sinai in 76, where they considered Schrödinger equation with quasi-periodic potential, and for the first time they proved that for small coupling constants there is absolute continuous spectrum present in the problem. So they managed to construct eigenfunctions of continuous spectrum for this equation, and that's actually a hard problem. So the Schrödinger operator for me will be L acting on a, so it will be discrete Schrödinger operator. Psi n will be L2 sequence, and then for this L2 sequence operator will be defined as minus psi n plus 1, minus psi n minus 1, and then I will write it as a plus lambda v theta plus n alpha times psi n. So if I add 2 psi n, it will be discrete Laplacian with minus sign, so it will be positive definite then. And then it's potential, quasi-periodic potential with quasi-periodicity constant alpha, which is assumed to be irrational. And theta is a phase. So there are 3 parameters at theta, alpha, and lambda. Lambda is a coupling constant. They all play different role. It's very important that alpha is irrational, and dependence on theta is kind of less important, but still important. Lambda is very important. So if alpha will be rational, that will be a periodic Schrödinger operator, and there are classical papers of Flaquet and Bloch describing absolutely continuous spectrum for this operator, and the structure of zones for this operator. So it's absolutely classical stuff. And so what Sinai and Dinaburg, and this is Dinaburg Sinai in 76 did, they consider small lambda, and they prove V was smooth potential, smooth, analytic, and then for this case they proved that there exists a component of absolutely continuous spectrum here. At least one component. Maybe they didn't exclude other presence of, say, other types of spectrum here, but they proved that there exists component of absolute continuous spectrum. And the proof was actually KM type of proof. And that's why lambda less than 1 is very, very essential here. And basically, idea is very simple, but realization maybe not so simple. That was the first essence when Km was applied in not dynamical setting, but in Schrödinger operator setting. So basically, if you look at this equation and you want to write that lambda psi n is equal to E, which is eigenvalue psi n, so you want to discuss eigenfunction for this equation, even if they don't exist, maybe eigenfunction of continuous spectrum, which are not decaying, because phi n is a L2 sequence, but just maybe order 1. Then you get equation that, obvious equation, minus psi n plus 1, minus psi n minus 1, plus lambda v, theta plus n alpha, psi n is equal to E to the psi n. And you can express, from this equation, you can write it in a matrix form, connecting pair psi n plus 1, psi n, with the previous pair, psi n minus 1. And then there is a matrix here, which I write down. It will be lambda v, theta plus n alpha, minus E, that would be the top element, minus 1, 1, 0. So it's SL2R matrix, which is essence of Schrödinger operator. And if you want to, if you start with the initial pair psi 0, psi 1, so psi 0, psi 1, then you can calculate what's going on here. But of course, you have to have function going for n positive and negative. So that is, you can reduce problem to studying of this cocycle. So you have a rotation of a circle and matrix valued function on a circle, and this matrix valued function will be S E theta, which is just lambda v on theta minus E minus 1, 1, 0. And then you have to study products of these matrices along trajectory of rotation of a circle by angle alpha. And if you understand this well, then you can say something about spectral properties. And so what Dinaburgis and I did, so what it is here, it is a function on a circle, right? A matrix value function on a circle. And if this function will be, if this matrix will be constant matrix, then we know how to study powers of constant matrix. So idea is to reduce it to constant cocycle. So change the variables. So we have one matrix sitting at theta and another in theta plus alpha. And so you can think that this matrix acts on R2 at this point, and there is R2 at every point of a circle. And so you change the variable, depending on theta in such a way that you have equation that if you change this variable and then you multiply by this cocycle S E theta, and then you take B minus 1 theta plus alpha, then you get constant matrix. Constant cocycle. If you can do this, it's a reducibility property, and then you know you're in a good shape. And they proved that for small lambda, there is small denominator, small divisors problem here. You can handle it in Km type, and you get this result that this thing exists. Now, it would be maybe less interesting if spectrum will be absolutely continuous always, but spectrum is not absolutely continuous always, and that's a completely different part of the story. To prove that instead for lambda very large, there is pure point spectrum. So when lambda is large, then you don't have these eigenfunctions of continuous spectrum, but you have decaying, in fact exponentially decaying eigenfunctions with certain eigenvalues. And that was also done by Sinai in his paper in '87, and then it was done in a more general, or in similar case, but with a slightly different technique. It was done by Fröhlich, Spencer, and Witter in 90. I think it's 1990. It's written somewhere. Yes, same P90, yes. And so they prove this statement that for large lambda, so there is transition from pure point spectrum to pure from absolute continuous spectrum to pure point spectrum, and that is manifestation of what is called Anderson localization. And that was very popular topic and still is in mathematical physics, physics and mathematics, meaning that if you consider Schrödinger equation, but instead of function which are quasi-periodic, put random variables here, independent sequence of independent random variables for different n, then for any lambda, spectrum will be pure point. And so what it says, that of course this is not a random sequence, it's just ergodic transformation, so it has very weak stochasticity properties, but for large lambda it's enough to create eigenfunctions of real eigenfunctions will be exponentially decaying, and that's transition. Now these two papers created a huge literature later on. I mean, Eliasson changed the whole thing dramatically. He proved that it's not just component, it's just really absolutely continuous spectrum. And then it was a lot of achievements here, soft and hard. So the most studied case is what is called almost Mathieu operator, when this V is just cosine. So I would say, maybe if I would have time, a few things about, so if f of theta is equal to cosine 2 pi theta, then this is almost Mathieu operator. And then in this case, everything, basically almost everything is known about spectrum of the operator. There's a certain miracle happening for this thing. But so far, spectral theory in the general case still is a little bit of a perturbation type. For small lambda, you know the spectrum is absolutely continuous. For large lambda, you know the spectrum is pure point. And there is not much information in between, although Arthur Avila did a good job of extending it to, from this case to general analytic function case, and he got Abel Prize for partially for that. But that is the state of art here. Okay, now I'm switching to another topic, and now I'm talking about Aubry-Mather theory and global KM. So, like, middle of 70s it all started, and I'm switching now to Aubry-Mather theory. So, I mean, KM theory existed already from middle of 50s for 20 years, 20 plus years at that time, and it also was perturbative. So, if you have small perturbation with the Taylor system, you know that there are a lot of invariant tori. So the next big step was Aubry-Mather theory, which started to discuss global properties. I mean, not only small lambdas, but for all lambdas, you manage to construct certain invariant sets corresponding to quasi-periodic motion. So I will start with a standard map. At that time, in physics literature, it was called Chirikov map. Even now, people sometimes use it for particular value, basically corresponding also to cosine. And so the map, which I will write down in a convenient way for myself, will be the following. So it will be cylinder map. It will be coordinate z and coordinate x. X will be periodic coordinate 0, 1, and z is from minus r to r. So x is a phase and z is a velocity. And this is the map will be the following: zn plus 1 is equal to zn plus f prime xn. And here you have xn plus 1 is equal to xn plus zn plus 1 mod 1. So this is derivative of some f is a periodic, smooth periodic function. Smooth periodic function, potential. You can think about this as potential, then its derivative, space derivative is a force. So what's happening here is that z is a velocity. At that moment of time n, you kick your system with certain force and you change velocity. So acceleration, which is difference with velocity, is equal to force. And then you apply this new velocity and you get new point, and that's how map works. And this is a map of a cylinder, area preserving map, and at that time people were saying zero Calabi invariant. So if you have a curve, it will not go systematically up and down, because up and down is still area preserving. So you might have, and you will have here, invariant curves. And what KM theory would tell you, and I would put parameter lambda here again, that for small lambda you will have a lot of invariant curves. And these invariant curves will be characterized by rotation number of them. So gamma rho is a rotation, is an invariant curve with rotation number, let me put it alpha, to be consistent with the previous, rotation number will be alpha here. So points here just move along this circle, along this curve. This is a smooth curve on a cylinder. And if you go look down on a, say, it's one-to-one correspondence, I mean it projects uniquely here. And if you look at the map on the x-axis, this map is a diffeomorphism with circle with rotation number alpha. So alpha characterizes this curve, of course, depends on lambda, and exists for KM theory only for small values of lambda. And so next big thing which happened was Aubry-Mather theory, which was saying that in fact you can have variational description of this object of invariant curves. And this variational description valid not only for small lambda, but for all lambda. So then what you do, you start with some functional A, which I will call action. And so you have, if you have sequence of xn's, so it's kind of monotone sequence going from -infinity to +infinity of coordinates xn, although it's periodic, but I will think that I put them on a universal cover. So I take this sequence, and the functional will be the following. You take xn plus 1 minus xn minus a square. Parameter a will not play important role here, plus f on xn. And n goes from -infinity to +infinity. It's not a number, it's just expression. It's not a number because you sum too many terms here, but you can discuss what does it mean that this functional is minimized by this sequence. It means that if you change the sequence on finite number of spaces, of positions, functional only increases. And so you can start with the problem of minimizing this type of expression over all sequences of xn, and then Aubry and Mather, I mean, they prove that if sequence is minimizing, then it has certain slope, and this slope is a rotation number. So basically for any irrational rotation number, and for any lambda, they exist minimizing sequences of this type. Moreover, if there is invariant curve, so condition for this sequence to be extremal, not minimizing, but extremal. So you have to differentiate with respect to xn, and you will get xn plus 1 minus xn minus a minus its derivative of this term with respect of xn. You also have xn minus 1 term, which you also differentiate. You get xn minus 1 minus a square. Sorry, not square, plus lambda f prime xn. And this must be equal to 0 because derivative must vanish at the extreme point. And if you see a minus a and this minus a cancels, so this is really zn plus 1, this term, because it's a difference of velocity. And you get zn plus 1 with minus plus zn plus lambda f prime xn is equal to 0. So you get zn plus 1 is equal to zn plus lambda f prime xn, and that's exactly that equation. So to be trajectory of the standard map is a necessary condition for sequence to have potential to be minimizing sequence, but of course not all trajectories will be minimizing sequences, only some of that, but that is a connection. And then what Aubry-Mather proved that for all lambda there exists invariant set where dynamics is conjugated to rotation, and which consists of minimizing trajectories for minimizers for this action. And in particular, if you have invariant curve, then all trajectories on invariant curve are minimizing. And if you don't have invariant curve, so the picture here will be the following. So the picture here will be the following, that if you fix rotation number, say golden mean, which is popular choice, but you can choose any not extremely bad rotation numbers, any Diophantine rotation number. So for fixed alpha, what you'll see that for lambda less than certain lambda critical, you have smooth invariant curve, which is Km type of curve with rotation number alpha, and which will depend on lambda. So just analytic. And then you'll get critical value. It's not exactly what they proved, but let me put it here. Then what you have, you will still have invariant curve, but this invariant curve will not be very smooth anymore. In fact, it will be C1 probably smooth, but I don't think it's proved really C1 plus alpha smooth. So it's not too bad, but not analytic for sure. That is the critical case. And then after that, when lambda is greater than lambda critical, there are certain gaps where point cannot end up being here because f takes too large a value here, so you don't want to get to these points. And what you'll get is invariant counter set, which has certain holes, and it will be the main hole, say for cosine, and then this hole by dynamics, by the standard map, propagates along the thing, so there are infinite number of holes, sequence of holes coming here. So that is called contour I. And so that is a global replacement of KM theory, which kind of say the object exists always, but gets through transition. And this transition is very similar to transition we had here. It's transition from elliptic behavior here. And this is a linearizable case. Like in the previous case, it was reducible, which is linearizable. Also elliptic. Through transition point, which in physics, in terms of Schroedinger, calls mobility H, which I'll say in a moment why. And then to the case, so you cannot say here whether it's elliptic or hyperbolic, but here it's hyperbolic. The trajectory, dynamical trajectory here on this counter set are hyperbolic trajectories. And again, I'm not sure that all the statements I'm saying are proved, but they are correct. I mean, this is a transition here, and that was a picture. So this object exists. The fact that it is hyperbolic immediately after transition may be not proven yet. But for large values of lambda it is proved. It's called anti-integrability limit. And that is a picture of transition from elliptic behavior through critical case to hyperbolic behavior. In both cases, because the presence of eigenvalues for Schrödinger equation is also hyperbolic behavior. When you have certain pair of phi 0, phi 1, which will decay exponentially when you apply this cocycle, when n goes to 1 infinity, n goes to minus infinity. It's not quite hyperbolic because stable direction and unstable direction coincide in this case. It's the same pair which produces decaying sequence in one direction, another direction, but it's a border of hyperbolicity case. So it is, morally, it is hyperbolic. I would also say the word renormalization, how it comes here. It was very interesting papers or work done in this case when lambda is equal to lambda critical, and that's renormalization which was studied by Mackay and many other people. Again, renormalization in area preserving case is basically was not done until very recently rigorously. Maybe it is done now by Hans Koch, but it's much harder case than Feigenbaum universality, which was actually studied more or less at the same time at the end of 70s. So there is very interesting renormalization behavior on this curve. The scalings on this curve are very non-trivial, and you get multifractal objects. So it's very interesting subject, but it's difficult to study. All right. So what is the connection with these two things here? And so one of the the connection I want to discuss is the following: that we derive this equation, which is a standard map equation for this action, as a condition for sequence to be extremal. But I said that not all, so any trajectory of standard map is extremal trajectory for this action. However, not all of them at all are minimizing trajectories. So what you will do next to study whether sequence xn is minimizing or not, you would look at the second order approximation. So the condition that it is extremal means that in first order approximation, if you perturb it in first order, it vanishes. But second order should be positive definite, and then you have minimum, right? So if we look at this situation, and this, so I'm coming back to my functional. If somebody will show me, yeah, it's here. So if I look again at my functional and just look at the second order expansion, what I'll see is that, so what I'll take, I have some sequence xn, and then I have sequence xn plus hn, and this perturbation of this sequence, and then I calculate the action of on one of them and subtract action on the other. And I want to see what will be the difference in the second order approximation. So see that I will have terms sum of 1/2 xn plus 1 plus hn plus 1 minus xn minus hn minus a square plus sum of xn minus xn minus 1, xn plus hn minus xn minus 1 minus hn minus 1 minus a square plus sum of fxn plus hn and minus sum of fxn. And I know that in first order approximation in H, this vanishes, all terms cancel out. So I just need to write second order terms. And the second order term here will be, from this term it will be just, so it will be hn plus 1 minus hn square, 1/2. And here it will be plus 1/2 hn minus hn minus 1 square, plus here it would be 1/2 second derivative of xn hn square, and then sum over n. And so I can collect terms which contain hn, and it will be just product here. So it will be minus hn plus 1. I put 1/2 of it, because second half will go to the product hn plus 1, I mean, which I will collect for hn plus 1. And then I would have minus hn minus 1. And then I would have this term, xn, hn, and all this is multiplied by hn. And so that is a sum over all n, and that is a correct answer. And then you see that we get Schroedinger operator in terms of hn. So what we get here is 1/2, and then we have Schroedinger operator L acting on hn plus 1, on hn sequence, scalar product with hn. And you think about hn as L2 sequence. I mean, this is pretty basic. So that's what you get. And actually it will be L, I took it with minus, so it's positive definite here. So everything is all right. So you want it to be positive definite, and that's condition for the sequence to be minimizing sequence. Anyway, what it tells us that, remember what is going on here. So AXN is a quasi-periodic sequence. Either it lies on an invariant curve, or it lies on a Brillouin contour, but it's quasi-periodic sequence. So it can be written, the thing, as a certain function on n alpha plus theta, if this quasi-periodic sequence with quasi-period alpha. And this is really Schrödinger operator with quasi-periodic potential. So it's another, this will depend on lambda, not in linear way, of course. So it will be another way to discuss a family of quasi-periodic Schrödinger operators parameterized by parameter lambda, which is not coupling constant. It comes in non-linear way here, but it corresponds to coupling constant in the standard map. And so for every value of parameter lambda in standard map, you first have minimizing sequence xn coming from Aubry-Mather, and then you want to look at the corresponding Schrödinger operator for this sequence. And so the conjecture which we try to kind of step by step to follow, to study, is the following: that in terms of corresponding Schrödinger operator, this transition from elliptic to hyperbolic behavior also has the same manifestation. So when you go through transition from smooth invariant curve to critical invariant curve to contour, the corresponding Schrödinger operator goes to transition from absolute continuous spectrum to singular continuous spectrum, and then to pure point spectrum. And I must say that this function phi will not be smooth when you go to the critical curve. It will not be smooth. It will have discontinuities when you go through the contour, but it is still quasi-periodic Schrödinger operator. And so that is what we're trying to do. And let me see. And there are some results in this direction, but so I would first say result, which we proved, and then say why I believe that the conjecture is correct, that there is a transition here, and why I think it's an interesting problem. So it's a joint with Martin Will from Toronto now, but he was a PhD student of Arthur Avila, and also with Arthur. Also, I was not able to check with Arthur whether he agreed that it is with him, but we discuss it with him definitely. It's just difficult to get hold of Arthur sometimes, but I will do. And so the statement is the following, that so suppose gamma alpha is a smooth invariant curve. Curve for standard map. You can think analytic, but actually we can do finite smoothness as well, but it's a little bit harder, just a little bit harder. Then this is kind of the Dinaburg-Sinai type of statement. Then there exists epsilon positive such that on 0 epsilon the spectrum is absolutely continuous. Is absolutely continuous. So we cannot, it's like Schroedinger, we cannot say that all the spectrum, yes?
So I'm not sure I understand the assumption. I mean, the standard map, you have gamma alpha, which is for some.
So you fix some V, and you have standard map.
So you fix some V,
yeah,
and therefore also some lambda.
Yeah. Some, but I'm not saying it's small lambda. It's any lambda for which invariant curve, smooth invariant curve exists. In this, okay. So we start with standard map. You can start with standard map and say, suppose there is an invariant curve for this. Or you can start with a curve and say, suppose there is a standard map for which it is invariant curve. It's up to you. Okay. But alpha is a rational number. Any. But actually, no, I would say I would have the Diophantine condition here as well. Condition as well. And then the statement is that there exists a component of absolute continuous spectrum. Actually, Diophantine was, it's also similarity with Dinaburg-Sinai because they also, of course, had Diophantine condition of rotation number. Yes?
Sorry, but so it's not one curve, it's a family depending on lambda?
It is family depending on lambda, yes.
Then the epsilon.
If there is a lambda, if there exists, for some lambda, there is this smooth invariant curve, then corresponding Schroedinger operator on this invariant curve, for any trajectory on this invariant curve, we have absolute continuous spectrum. And epsilon will depend on lambda, of course. So basically, curve and standard map define this epsilon.
What is this interval, 0 epsilon?
So this is okay, the spectrum cannot be negative there. Spectrum starts at 0. And so we are proving existence of absolute continuous component near the edge of the spectrum, right? It's positive definite because otherwise it's not minimizing trajectory, but it really starts with 0, and I will explain why. So 0 is essential part of this thing. Okay, now let me explain what is behind this. I mean, so first of all, this is, as I said, it is not a local statement, it's kind of global statement. Just as long as you have a very smooth curve, you have this property. But what is behind it? So let me give you a simple explanation, but the proof is not exactly what I'm saying, but it will give you motivation of what's going on. So you have invariant curve, smooth invariant curve, right? Now you can take any point on this invariant curve and start trajectory. And all trajectories have the same nature. I mean, they're all the same, and they're all minimizers of this section. So if you have one smooth one parameter family of minimizing trajectories, then you can differentiate with respect of this family, and you will get vector for which your second order operator vanishes, right? So you can differentiate with respect of this curve, with the starting point of this curve, and we'll get vector Hn, which will be bounded That's not trivial that it will be bounded, but it follows from Riemann theory that this vector will be bounded. So if you differentiate it, then perturbation H0, H1, and so on will not be growing. It will be bounded by constant. So it will be eigenfunction of continuous spectrum. It's not growing, it's not decaying. And you can construct this function, eigenfunction Hn, just by differentiating the thing. Concrete eigenfunction is a property that L vanishes on it. So you can construct eigenfunction of continuous spectrum for eigenvalue 0. It's not eigenvalue, but it's part of continuous spectrum. Now that's not enough to say that your spectrum is absolutely continuous. You have to have many of such eigenvalues for which you have eigenfunction of continuous spectrum. So you have to work to say that you can perturb things, and still for the E, for the energies lying in this interval, you still have eigenfunction of continuous. And this requires a work, and this is done, a lot of work done by Avila, and almost reducibility is important part of it. It's subcritical. You can show that Schroedinger cocycle here will be subcritical, and this is an open property, and because of that you can perturb it, it will be still subcritical, and then you can reduce, say that you have almost reducibility, and then you can conclude, make this conclusion. So that's more or less how the proof goes. But it's not very hard, but requires some work. But for example, we don't know whether there are no eigenfunctions for other values. So we don't know things about the whole spectrum. We know only part of it. Now let me try to explain why I believe that for situation of Cantori, the spectrum will be pure point, or at least it will have component of pure point spectrum. So I'll be happy to just construct one eigenfunction for that situation. Okay, so that would bring me back to the old 80s, when this topic was very popular. And why this topic was popular, what's relevant for this conference? Because this transition, which I said, transition from elliptic behavior through critical behavior to hyperbolic behavior, that was considered as a transition from order to chaos. Because whenever you have invariant curves, there is no transport from this part of cylinder to that part of cylinder. The point cannot go through. It's kind of not obvious because it's a map, so maybe you can jump out, but no, you cannot, because if one point goes sometime here, then you can go very low in the cylinder, and then connect this point with that, and then this point will still be below, so it will be intersection of the image with the thing, which is impossible. It's invariant curve. So you cannot go, when you have invariant curve, from low part to upper part, and so transport properties of points by dynamics from low part to it's bounded by these invariant curves. However, if there are no invariant curves left, and what people believe is the last curve will be golden mean, so when parameter lambda increases, all curves will be destroyed at certain moment, so it will be no invariant curves which are projecting on a base. You have this counter set. So you have this hole. And I said it's hyperbolic orbits. This counter set consists of hyperbolic orbits. So these endpoints of this gap play important role. And what people are constructed, they can construct stable and unstable manifold for these 2 points. So that is called turnstile. And so you can construct one curve. Let me do it colored. One will be stable, so it will be curve. When you iterate forward with your map, this curve will be getting smaller and smaller, decaying, and connecting holes when you iterate forward. But if you iterate backward, it will be still connecting gaps, but will be crazily kind of oscillating. And there is unstable curve, which also connect these 2 points. When you iterate backward in time, this will be smaller and smaller, but when you iterate forward, it will be crazily. So instead of invariant curve, we have these 2 curves, stable and unstable manifold, and they call what is called turnstile, like in a subway when you go through. Why is that? Because when point go from low part to upper part, now it's possible, it must pass through this turnstile. When you go forward in time, when you go from lower part to upper part, you go through one of them, and from this part to that part, you go through another one. So the size of this turnstile, people were very interested in it, characterize the transport properties, how much of transport you have through the thing. And so the aim is to construct eigenfunctions. So remember what was eigenfunction of continuous spectrum. We were just differentiating along this thing. Now you cannot differentiate here. You have hole. It doesn't have. But idea is that you can adjust it and create Hn, which will be decaying both in positive and negative time. And that will be candidate to be eigenfunction for the, again, for the edge of the spectrum. Because in this case, when you consider Schrödinger operator in this case, it is what is expected that this is greater than constant, that it is not greater than 0, but it is greater or equal than some constant greater than 0. And this will be a normalized sequence of L2 sequence of norm 1. So that there is a gap in spectrum. So when you go through this transition, the spectrum will start not from 0, but will start from certain E, and then goes further. There is a gap in spectrum, and the gap in spectrum of Schrödinger operator actually characterizes hyperbolic properties of the trajectory. To say that the trajectory is hyperbolic is the same thing to say that spectrum of Schrödinger starts with certain E greater than 0. That's well known from 80s. And so what we want to prove that this E is really eigenvalue, and construct eigenfunction corresponding to it by dynamical means by perturbing the thing and creating this eigenfunction. And I think it's doable, but it's not done yet, and it is a work in progress. And maybe I'll just finish by for those who don't know, it would be kind of amazing, but for those people who know, it will be still quite nice. I will formulate how much people know about spectrum of Schrödinger for the almost Mathieu. And of course, we don't hope very soon to be on the same level of precisionness. But what is known for Navier, for almost Mathieu, so it's L psi n is equal to minus psi n plus 1 minus psi n minus 1 minus lambda cosine two pi and alpha plus theta psi n. So it's almost Mathieu operator, Schrödinger operator for concrete potential cosine. And for this case, there is a miracle happening. And so what is known that for lambda between 0 and 2, the spectrum is absolutely continuous. So we know until when it is going. For lambda equal to 2, the spectrum is singular continuous. Now, it's known for almost all theta, you cannot exclude countable set of exceptional values of theta where it's not true. It's expected that there is no exceptions, but it's not proved. But basically for almost all theta in alpha, the result is valid. And then for lambda greater than 2, the spectrum is pure point with exponentially decaying eigenfunctions. And then it is known for almost surely in terms of alpha and theta. And here it is known that there are some exceptional values for which it's not true. There's a way to describe it, but for almost surely it is pure point. So there is a miracle happening, and it's a lot of work done by Lana Zhytomyrskaya, who actually studied this. And in fact, many results can be obtained on a kind of soft way, using soft methods. Not all, but many. And this value of lambda equal to 2 in physics is called mobility age. So mobility age, because Schrödinger equation is supposed to describe the movement of electrons in these one-dimensional systems. And so what it means is that if you have absolutely continuous spectrum, then electrons can move freely through the system. If the spectrum is discrete with its exponential decay, then it is, the electrons get blocked, they cannot go. So that is a transition from a conductor through this mobility age where electrons start to move. After this value, they start to move. This is isolator here, and this conductor, and that's why physicists are very much interested in this type of transitions in systems, because this transition from isolator to conductor. And let me stop here.
So, are there any questions?
So I'm curious about the exceptional keys. Are they arithmetic nature?
There is arithmetic nature.
Known that it's singular continuous in that case?
I don't remember. I think it is, you mean in this case, right? Let me see a bit. Yeah, I think it's not absolute continuous. Yeah, I think it can be occasionally it can be singular continuous. Yeah, but I have to double check it.
You mean the exceptional?
Exceptional values here in this case there are exceptional values.
Okay.
Here they expected not to have exceptional values, but here there are exceptional values. Dima?
For continuous time, Lagrangian systems, you expect similar behavior?
We haven't looked at it, but it would be kind of natural to expect it. Yes, I mean that for continuous time. Yeah, I guess so. Yes. Well, there is always this kind of. You can look at the. I describe Schrödinger equation in discrete time, and then actually initial paper of Dina-Borg-Sinai was in continuous time. It's not much difference. I mean, usually you can translate result from one story to another story, but technically they can be a little bit different. And the usual perception is that if you can do something in discrete time, you can do the same in continuous time. I would expect yes, but we didn't look at it.
Okay, so what I would like to do today is somehow take you back to the 80s. Because most of what I'm going to talk about is actually uses tools that were developed in the 80s and maybe have not been used properly in the context I'm interested in. So what I'm interested in this talk is the motivation is twofold. The first motivation is I like to somehow understand good properties of, say, non-uniform hyperbolic systems. And that means so that are so good that first of all apply to my favorite non-uniform hyperbolic systems, which is the Teichmüller flow on a component of a stratum of abelian or quadratic differentials, and the geodesic flow on a closed rank-1 manifold. So it should apply hopefully to both setups. And the second motivation is I like to understand the following question. When you look at a random walk on a group, you have very strong properties. In particular, if you have a representation of the group and you can talk about somehow the stationary measure and get very strong properties concerning simplicity of Lyapunov spectrum and so on and so forth. And so my motivation is, can you somehow have similar properties for measures where you don't know that they come from random walks, but maybe in a more general setting. In the more general setting, again, I mean, what I have in mind as an application is a Teichmüller flow on a component of a stratum of abelian or quadratic differentials and the Maser-Veach measure. And so I want to derive something like simplicity of the Lyapunov spectrum for, say, a co-cycle coming from a representation of the mapping class group into, say, this target. This is in a simple Lie group. This is very general. And so the verdict is that this works. And I will try now to explain to you a little bit why this is the case. And this really is using tools from that were developed in the 80s. But let me first start with a more elementary part. So I'd like to understand so non-uniform hyperbolicity. So now what I mean is by this, start with something very familiar, the shadowing and a loss of closing. So probably all of you have heard about this. It's really also a concept that's actually from the probably 70s. This was introduced, shadowing and loss of closing. Shadowing was introduced by Rufus Bowen in the 70s. So we take a smooth flow. So later on I will not even have a flow anymore, but for the moment we take a smooth flow on an orbifold. So, I mean, orbifold seems to be contradicted. The flow is smooth, but I mean, this can be made sense out of it. And then we know what a pseudo-orbit is. And what I like to do is I want to take a collection of sets where these sets run through some index set. And this index set for basically all the time will be actually a finite index set. And so these are supposed to be open and contractible. And then I'm going to do the following. I take points qi in V, say I of j of I somehow. So in one of these sets, and times ti bigger than n, where n is a given number. I should write it up here, M pseudo-orbit. So n is a given number, think of it as large, and then I want that phi ti qi is contained in v j I plus 1. So in other words, so the orbit goes, so I have here one of my sets, so I take my point qi, then I land in, so this is my set, my first set there, v alpha, and this is the set v beta, and I land in the second set, and then I have another point in the same set, and I start flowing again, and this is a pseudo-orbit. And what I want is that, traditionally I want that this is actually fellow-traveled, uniformly fellow-traveled by an orbit. But this seems to be too strong a requirement. So in the setting of Teichmüller flow, you can never be sure whether orbits actually are stay close to each other properly. So we may not want to do this. The idea is that this corresponds here an orbit, but we may not wish to impose something like Hausdorff close or something like this. So rather I may wish to take a topological control. And then we are happy in the setting that I described before, which will be good enough. So suppose we have a group G, so think of it now as a fundamental group, the orbifold fundamental group of your orbifold, or think of it in the setting as I described before, say the mapping class group or whatever it was, so that the following holds true. So each periodic orbit for this flow phi t corresponds in a unique way to a conjugacy class in in G. And so I also want that conjugacy classes of distinct orbits are distinct. And now you just can do the following. I mean, you connect, you do what you always do. You connect these 2 points, so the endpoint of your first orbit segment, you connect it to the starting point of the second. So you produce a closed curve. And what you want is, so you find a closed curve. So this connection here is supposed to be entirely contained in this contractible set that you started off with. And you want to find an orbit such that this orbit, we don't want it necessarily that it fellow travels, but somehow that it captures the topological property here. So first of all, it passes through the sets V, Ji in consecutive order. And then the element of G defined by the orbit is determined by the pseudo-orbit. In this I was about to add, of course, now I want to have the pseudo-orbit is closed, if the pseudo-orbit is closed. So in other words, I do allow that the sort of these orbits or orbit segments deviate somewhere in between the sets. That's fine. But I want to come back, and I want to also have an identification of this pseudo-orbit with an actual group element. So the main example that I have in mind here is, I mentioned before, so main examples are twofold. So first is the Teichmüller flow. If you don't know what that is, this is completely going to be irrelevant for the rest of my talk. It's just the main example. The Teichmüller flow on a component of a stratum of abelian or quadratic differentials. And the second example is the geodesic flow on a rank 1 manifold of non-positive curvature. So this manifold is closed of non-positive curvature. So this is somehow a good shadowing property that you would like to have, and this is satisfied for the examples that we were looking at. And so now we will see what we can do with this. So what we want in addition, so now comes what I like to describe as uniform hyperbolic localization. This is going to be the property that this looks a bit funny. How can it be uniform in localization? But you will find out in a moment. This is a property that does hold in both examples here. And this you all see is exactly what gets you going with basically having this property, you can prove all sorts of things that you know for hyperbolic flows or another flows on a nice smooth manifold. So what we like to have is, so we like to first of all have a measure, lambda, probability, invariant. And then this should be absolutely continuous with respect to some nice foliation. So the foliations don't have to exist everywhere, but we want somehow some pacing set if you want. So near almost every point we would like to have these foliations. And so we have, so let me make the following requirement. We have strong stable. As you know, in this example that I mentioned, there exists on the nose, so to speak, strong stable and unstable foliation, strong unstable foliation. WSS, WSU. And now we take a typical point for our measure. So take a Q, a good point, and good in some sense can be anything. In practice it will be a recurrent point. So it can be, in other words, it can be a typical point for any like invariant measure that you take, but in particular for the one that you were looking at. And you want that if you take such a good point here, then there exist small balls. Now take any metric on these stable or unstable manifolds. So the idea is that you have small contractible sets that are neighborhoods of these points in this strong stable and strong unstable manifolds. So let me call this B as Q, R, and B as S, Q, R. So that, SU, QR, which give you a product neighborhood, so product coordinates. Define product coordinates. So let me be slightly informal because you know this all very well. So what we do is we take this piece of strong stable manifold, we have a piece of strong unstable manifold, and then we take any point on the strong stable manifold and we take the holonomy map along the stable manifold, and then we get a piece of strong unstable manifold to that point, namely which consists of all points which have the same asymptotic, the same direct, so asymptotic to this point on the stable manifold, and in the same direction of the given leaf of the strong stable foliation. So this is the image on the holonomy map, and then you patch together, so you let the flow run a little bit, and then you patch together this neighborhood. Let me define this neighborhood by, say, this is determined by the setup here. It's a standard hyperbolic system construction. So this T0 is a flow parameter, so you have to flow a little bit with your flow to get some honest neighborhood. So we assume that we have some product coordinates, and we also have maybe a slightly bigger, let me call this V1, and we have V2, a slightly bigger such neighborhood, where we maybe take 1 plus R plus 1 plus epsilon, and this should be small so that the measures are nicely controlled. I will not give you the precise requirements on the measure, not to be too technical. And now the crucial property that we like to have is the following. There's a uniform property. Suppose that Z in V1 is recurrent. Okay, those points exist because recurrent points are everywhere. So let's assume the measure has full support. Then we have plenty of recurrent points under the flow. And now what we want is, then there exists a number which depends on this point Z with the following property, namely if T is bigger than this n of Z, and now comes the uniformity property, then, and phi T of Z is contained in this smaller set here. Then we can ask, what is the image of the stable and unstable manifolds? And then we want that phi T BSS of Z R times 1 plus epsilon is contained. And so we take this slightly bigger, strong stable manifold, and then we want to have it in be contained in the strong stable neighborhood for phi TZ, and similarly phi T BSU of Z R of 1 plus epsilon is contains BSU phi t Z R of 1 plus epsilon. And where the uniformity comes in, so the uniformity comes in, the n of Z depends on the point, but this property doesn't. So basically, so what it says is if you just wait long enough, then you will basically have complete hyperbolic behavior. So you will have exactly the property that you expect from a hyperbolic flow and an inertial flow, but you cannot have it uniformly in the time. You just have to wait as long, as it maybe takes. All right. And now you can see if you have this property, and if you have some additional control. Now, if this measure is very nice, for example, if the measure has a measure that you would expect from a Gibbs type measure or a measure of maximal entropy, namely that conditionals expand and contract uniformly under the flow, then you have complete control under these of the measures of these intersection sets, and then you can do orbit counting, and you can also have a control on Lyapunov exponents for co-cycles over the flow. Let me just state this more formally. So now let us assume, and in general, you don't even need this. You need some sort of Gibbs type property for the measure, and then you can, if you want, change the time of the flow and think of it as being some sort of measure which with uniform expansion where you get then the same result. But let us assume, and again, our favorite measures have these properties. They exist in number h because n 0 is such that we have conditionals lambda SS, lambda SU on these strong stable and strong unstable manifolds, and such that d phi t lambda SS over d lambda SS. So you flow the conditional measures, and then you get contraction with this constant here. This is e to the power minus ht, and you flow the strong unstable measures with the flow, and then you get uniform expansion. And under this condition, you can see that you get, if you take a recurrent point, you wait long enough, you get complete control on measures of intersection components containing the point and the returning point. And so this allows you to count and get a control. So this allows to count orbits, as you do in Margulis's work, exactly in the same way. And also you can have a control on Lyapunov exponents. So what I mean by this, let me now talk about flat bundles. So this is basically a co-cycle over our flow, which is given by some particular nice situation where the fact that we don't know that orbits are really fellow traveling, so pseudo-orbits are really fellow traveling closely, orbits is irrelevant. So what we take is flat bundle. So assume that my setup is m is equal to m hat mod this group G, and there exists E, a finite dimensional vector space, and G, H, subgroup of GLE, a simple Lie group. So think of it as an algebraic group. You don't have to be a GLE, can be a symplectic group or something else. It's just a simple Lie group of non-compact type. And then you can do the twisted bundle construction. So you can form M hat cross E. So now you have this representation, though I forgot to say you have a representation psi of G into H. And now you can take the twisted bundle construction. So you take the product space here and you divide it by the action of G. You get a flat bundle over M. And then you can look at the corresponding co-cycle. So you extend the flow phi t to a flow on E, geometrically speaking, by parallel transport. For those who like abelian or quadratic differential, this will be by the Gauss-Brownian connection. For others, this will be something else. And so you can extend the flow, and you can talk about Lyapunov exponents. So you have this invariant measure, and so you always assume that it's finite, and it's now let's assume that this co-cycle is integrable, which in good cases will be. And then you can talk about the Lyapunov exponents. Say kappa 1 bigger or equal than kappa n. And now what you get immediately from this uniform recurrence control is the following control on Lyapunov exponents. You know that, so for each periodic orbit, gamma, you get a return a holonomy map. Say alpha of gamma, by just going around the orbit once and looking at what happens in the fiber. And so you get absolute values of eigenvalues, so have absolute values of eigenvalues. And now, say, if you denote this by, say, kappa 1 of gamma bigger or equal than, and so on and so forth, kappa n of gamma, then you can derive the following statement, so a proposition. So typical, and I explain what that is supposed to mean. Typical is that this gamma, this kappa I of gamma minus the Lyapunov exponents for the system is less than epsilon, for epsilon given. And typical means here for the proportion of periodic orbits with this property of length less or equal than r. So now you sort them by the length of the periodic orbits. And now you look at those which have this property. Overall, a periodic orbit, this tends to 1 as r goes to infinity. All right. Well, that's relatively easy. So you can see that this uniform hyperbolic localization gives you incredibly strong conclusions. And this is completely general, so you don't need basically any particular setup. As long as you have this, you can get going. But now let's try to understand what happens with these Lyapunov exponents. Can we prove under suitable assumptions that we have simplicity of the Lyapunov spectrum? All right. So let me state first the result of Avila and Viana in 2007. So what they proved is, and now I'm sort of going a bit slower because now we have to import some kind of a little bit more complicated concepts from the 80s. So let me first state what Avila and Viana proved. So Avila and Theorem. So they look at the representation from the mapping class group, so the mapping class group of a surface of genus G, and into the symplectic group. And what is this supposed to be? So the mapping class group is this group of isotopic classes of diffeomorphisms of your surface. Each such diffeomorphism acts on the first cohomology, which is a 2G dimensional, so with real coefficients, 2G dimensional real symplectic vector space, symplectic form coming from the cup product. And you can look at this representation. And so what they proved is that if you take this representation and then you look at this extension of the flow, so look at the extension of the flow phi t to a flow on this flat bundle, where phi t is a Teichmüller flow on a component of a stratum of abelian differentials. And lambda is a so-called Maser-Veach measure, so it's in the Lebesgue measure class. Then the Lyapunov spectrum is simple. All right, so that's a very nice theorem, and they prove it using a tool that's called Rousey induction, whatever that means. So now I like to somehow, in some sense, explain to you, or try at least, what kind of a philosophy you could make behind this, forgetting about Rousey induction. So the first observation here is, how can you have a simple Lyapunov spectrum if the target of your group is contained in a small subgroup? You will never get a simplicity of the Lyapunov spectrum. That's not possible. So you need somehow the target to be big. And what means big is big. Yeah, big could mean Zariski dense, whatever that means. So you somehow need that if you try to find the smallest Lie subgroup that contains the image here, it had better be everything, otherwise you cannot hope for simplicity of the Lyapunov spectrum. I mean, if you end up in, say, the trivial group, how can the Lyapunov spectrum be simple? I mean, this is impossible, right? I mean, there's nothing happening. So you have to have some sort of more complicated situation. So that's one constraint that you have to somehow impose. So you need, if you have such a homomorphism here, or more generally, say you look at a rank 1 manifold of negative curvature or anything else, right? You have this somehow this homomorphism. You had better impose a condition that the image is large, it's big. All right. So in this case, somehow the image has to be big, but you still have to prove something. So let me mention the result of Gutierrez, Romo, Gutierrez, Romo, who showed he somehow explicitly, in some sense, explicitly computed what the image is. So of course the verdict is this has to be big, but he confirmed, okay, it's big, and he actually computed what you get. where this has to be slightly reinterpretation. This homomorphism is surjective. But now you look at these strata and you have to get a proper reinterpretation what it means, so that this the topology of the strata, or whatever you say here, is connected to some big subgroup of this symplectic group. So, all right, I don't state exactly what he proved. Anyway, so now let's shift gear, and I'll try to show you that this is a very general, it's a sub result of a very general theorem. So let me state the very general theorem, maybe just in the case of this Teichmüller flow. All right, so theorem, take any, you can also take a rank 1 manifold and look at the homomorphism of the, whatever the fundamental group is, very general. Take any homomorphism psi of modus into G subgroup of GLE with Zariski dense image I'm slightly lying here. You really have to sort of look at this condition if you restrict somehow your setup to these strata which are not so well understood. But let me cheat a little bit here and sort of state it slightly incorrectly in this form, because again, I mean, you have to be slightly careful about the image that you get here. Then you can form again, I mean, you look at the corresponding flow, so you take any stratum of abelian or quadratic differentials, any component, sorry. Then the Lyapunov spectrum is simple, of this co-cycle defined in this way. All right. So now, if you ever saw a random walks, then you would realize that it's actually a pretty easy statement if you knew that you start off with some random walk on some group. Because there's wonderful work, not only by Sebastian Guezel, but actually people that are much, much older than he is. There's wonderful work, I guess Sebastian is going to agree that this is wonderful, by Giorgi and Giorgi and Goldscheid, Margulis and others. Let me just put up the name. So Giorgi and Giorgi and Goldscheid, Margulis. And then there's work by Benoit and Benoit and Caen, and there's work by Guezel, and there's work by many other people. There's work by Kalmanovic, and there's an industry of results. And the punchline in particular of these works that were done around in the 80s, about the same time, the punchline is if your setup, so this is a philosophy, if your setup comes from the random walk, this statement of simplicity is free under this assumption. So you don't have to prove anything, you get it. Except that you have to be careful about what's supposed to mean the Lyapunov spectrum. But I mean, once you know this, then it's free. All right. So now I want to go backwards and I want to say, okay, I try to somehow copy identically what these people tell us for random walks, except that forget the random walk and replace it with something else. And this something else will be good enough to cover all these cases here. So, and this something else comes also from the 80s, and this is amenability of action. So let me define what this is. There was a lot of work on amenable actions done in the 80s. All right, so I mean this will be hard because now I have to clean and talk. So what is amenability? Let me define, this might look a bit funny. So I defined it in the topological setting. What we will be interested in is actually not the topological setting. We will be interested in the measurable setting. So what is this supposed to mean? Let's suppose we have a group gamma, a countable group. And let's suppose this acts on a compact space. X. And then you impose a condition that looks really pretty similar to what you would get from random walk. So the condition is, assume that there exists a sequence of maps Xn from X to the probability measures on gamma. We can suppose that these are finitely supported. So this is what is a probability measure on a countable group. It's just an L1 function which is non-negative. All right. So in this, there's the map Xn. So n is a parameter from X into the space of probability measures on gamma, such that. And now you can look at the probability measures being a subset of L1 space, as I tried to explain. So you can take the L1 norm, and so you want that the L1 norm of Cn of X minus Cn of, I messed it up, so there's two G, so the G acts on both sides. So you translate this measure Cn of X with G, and then you subtract Cn of Gx, and this L1 norm is supposed to go to 0 uniformly as n goes to infinity on compact subsets of X cross gamma. So X is already compact, so this means you fix a finite set of gamma, and this is supposed to be uniform in this finite set of gamma. So that is a bit funny condition. But there are lots of groups that admit such an action. Actually, presumably almost all groups admit such an action, but for us, most importantly, there are lots of groups that admit a very sort of well-defined, or say a very explicit such an action. And now here comes the fact that is due to Fürstenberg. So, assuming that we have nu an invariant measure class, on X. So this is not supposed to be an invariant measure, it's supposed to be an invariant measure class, so invariant for the action of gamma. And suppose gamma acts on some other compact space Y. So then Fürstenberg shows that there exists an equivariant, a measurable equivariant map from X to the space of probability measures on Y. I mean, the space of probability measures with the usual weak-star topology is some nice space. I mean, whether it's nice or not depends on your taste, presumably. But there's this equivariant map. So gamma acts here, gamma acts on Y, hence acts on the probability measures on Y, and you get this equivariant map. All right. So, and of course, now you might wonder what you can do with this, but you actually can do a lot. So what the verdict is now, what you want to do is, you want to show that and this is exactly what works in many good cases. So what you want to show is that actually, so P of y, so the images Cn, so let me call this f. F of x is a Dirac mass for almost every x. Then you get actually an actual map from x to y, which is equivariant. And then, of course, you can apply properties of your action on y. And what we have in mind for the question of Lyapunov exponent is when y is actually like a Grassmannian. So you have say a subgroup of GLE, and you take a Grassmannian of subspaces of E, which is a compact space. If the group gamma acts on E, then it acts on the Grassmannian. That's, I mean, this is a linear action, right? So, and then you can look at the situation here, and the simplicity of the Lyapunov spectrum will follow if you can prove that basically there's nothing, no mass accumulates on some subspaces. So you scan through all the Grassmannian for all the dimensions. I mean, this is finitely many, right? And what you want to say is you play this game and you never hit any sort of positive mass on some subspace, and then some general machine kicks in that you actually employ exactly in the case of random walks, which tells you then you get automatically simplicity of the Lyapunov spectrum, provided that this measure nu has anything to do with some flow measure or whatever you have here. I mean, this measure nu has a priori nothing to do with anything else, right? And now the end game is, of course, first of all, you want to show this, but the end game is also you want to specify more properties on these measures and relate these measures, these invariant measure classes here. It's not a measure, it's a measure class, right? In the case of random walk, you would look at stationary measures here, which is nice. But here we don't talk about stationary measure, we talk about something else. So more general, so what you like to do is you want to relate these nice measures here, measure classes, to some actual measures that come from a flow. Well, that's the end game. And now the only thing that you have to do is you have to go through the proofs of what you do in the random walk case, and you have to find nice conditions on your measure class that get you going. And let me give you some conditions. So somehow you need to relate, as I said, you need to relate this measure class to something that is actually like an invariant, whatever that means, invariant probability measure for some flow. I mean, so far we don't see any flow, we just see this group. And there is nothing, someone keeps on using the eraser. Oh. Oh, yes. Holding the microphone and erasing at the same time is a kind of dust. That is a little bit challenging. Sorry. So here comes a very general machine. This is complete abstract nonsense. But then you can realize that the good examples kick exactly in this framework. So what you want to know, so you want you to be nice. And now we have to understand what that means. So we want that, it's a measure class. Nu is athletic. All right, this is clearly a nicest assumption. You want a second property, which exactly mimics somehow that you want to somehow be able to separate points. Instead of separating points in the target, you separate points in the domain. So you want that for nu, almost every x in x, there exists a sequence Gi in gamma such that Gi star nu converges to the delta mass at x in the weak topology. This is exactly separation of points almost everywhere. So again, I mean, you want to have it in the target, but instead you impose it in the domain, and this will be good enough. And the third property is
you want that if there exists a gamma invariant periodic ladder measure on x plus x in the measure class. Of new person. Alright. Now if you think about your favorite example, this you always have this. You have conditional measures, you patch conditional measures together, you get something like this, so this you can make it invariant, here we go. And now you still don't have a flow. This is abstract nonsense. It's still abstract nonsense. You still don't have a flow. But now you just make a flow. So how do you make a flow? You just produce a flow, I mean on x. So you cross with r, and now you look at basically conditional measures. So you fix a model for your new cross mu, and you just make out a flow by imposing expansion conditions on your conditions. So my time is almost up, so let me just write down so I will not specify this, similar to what's called a Maharan extension that was also sort of investigated in the 80s. So it's not particularly relevant here, but so you want to look at construct the gamma invariant flow on x plus x plus r with finite. So ideally, this is not absolutely necessary. Ideally, this finite quotient. So quotient measure here you have this measure, this invariant measure, measure class of mu plus nu of x plus x, and then you take the standard vector measure on r. And so you want that you have this nice flow, and so the group acts, and you have your finite quotient measure. And now you can see that this is a model for all the spaces that we looked at. And now once you have this and this condition, which you have to verify in the examples, then you get going and you get simplicity of the Lyapunov spectrum in exactly the same way as you did when you studied random walks. And that's the end of the proof. Thank you for your attention.
Thank you very much. So, questions or comments?
Sorry, you said that these examples were relevant for the talk, but maybe can you explain what these results say, for example, for geodesic flow in the rank 1 case?
Yeah, so for geodesic flow in the rank 1 case, you can, for example, start with a unique measure of maximal entropy that has these conditionals. And then, I mean, you have the bounded infinity. I mean, this is not as nice as in the geometric case where the next curvature is negative, but it still exists. So the measure gives full mass to the good points, as I described before. I mean, good, nice points where you have these product neighborhoods and so on and so forth. So everything is good. You get this property here, these properties you get. All right, here you have you basically play the same game. So you get, I mean, you take a representation, the homomorphism of the fundamental group of your rank 1 manifold into whatever, right? And then you get simplicity of the Lyapunov spectrum for the extended flow with respect to this measure of maximal entropy. And if you knew that the back measure were ergodic, which you don't because it's an open question, then you could do exactly the same, because then if the back measure is ergodic, then it has to have conditionals absolutely. It has to be absolutely continuous. And then you can play exactly the same game and get this for these measures as well in general, and it gives type.
But if you knew what it is ergodic, it follows.
Sorry?
But if you know what it is ergodic, when it follows in particular what you simply.
Yeah, then you get the same, except the problem here is that you don't know that it's ergodic.
But you know in some cases.
Yeah, in some cases, if you happen to assume, just take it as an assumption, it works for this case as well. So this way, yeah.
in the logic of the argument. So when you have these three properties, you have to reprove the Goldstein-Margulis to do in different way, or just to follow it and.
No, you basically use ideas from the proof. Actually, more
okay.
so you pick some certain properties from the certain items from the proof in the paper by Goldstein-Margulis, and also in the paper by Giorgi, and then you set up this general machine. And then you prove, I mean, you have this condition, right? And then in the examples, you have to verify that this is a condition of the measures are satisfied.
Okay.
And that's it. But I mean, the idea comes really to trying to sort of understand what you really need to get the conclusion that you want, and then run somehow the proof, what they do, and just sort of change somehow the setup. It's not too complicated.
Okay. Okay. No more questions? Okay, so thank you again. So there is an announcement. So at 6 there is a poster session in the Scuola Normale. So I want you to explain where it is exactly.